So I'll be talking about routing models and how to train them. So in order for you to understand the title, I will start with this one-sentence introduction to what routing models are. So we have routing models are basically this framework for having neural nets that have conditional computation. So normally, when you have your standard neural net, it has a bunch of layers, so a bunch of these building blocks. You have an input, you pass it through all of these layers, you get an output, right? So if you do that, you sort of activate all of your parameters of your network. But you might want to be a little smarter. So in this cartoon view, you could say that each of these sort of rectangles is some building block, so some small layer, right? And then given an input, you will be routing it through some path of your larger computational graph, right? So you don't want to use all of your parameters for every input. You want to use only some part that seems relevant, right? And we'll be moving towards, obviously I will define it sort of more formally later, and we'll be trying to train these kinds of networks. Okay? So to give you an idea of what is this based on, so during 2 of my internships at Google, I contributed to 2 different research projects, and they correspond to these 2 papers. One of them is from a few years back, it was on iClear. The other one is pretty recent, from a few months back. Yeah, and they were very, very different things, but sort of both of them kind of fit under this umbrella of routing networks, so sort of routing through some path of your larger model, but they give sort of very different perspectives. And then obviously many other people did many other things. So here's a list of papers that I will be referencing during this talk, but don't treat it as a complete list in any sense. There are many things out there. Okay, so in terms of the parts, I will try to squeeze 4 things. So first I will define more formally what routing models are, what routing networks are. Then sort of talk in a high level how to train them. And then I will go into these 2 papers. So I will show with sort of technical details how did the methods in these 2 papers worked, and sort of what were the data sets, what were the problems, and like a highlight of results. So the most important number and some takeaways. And feel free to interrupt me if you get sort of confused during the talk. Okay, so routing model. So basically the image that I showed at the beginning, but with a little bit more structure. So we will have our larger graph. It will have some components in it. When I say component, I don't mean anything super specific. So let's say a component is just a small building block, so a linear layer or a fully connected network or a single convolution, a couple of convolutions, just a small part of a graph that has an input and an output, right? That's a component. And then we will have several layers. Each layer will have a bunch of components to choose from. And then for a given input, we will be somehow choosing some subset of components to use in every layer. So for example, for some input, we will choose component 1 and 3, because this input contains a cat, and these components are sort of cat experts. And then we'll pass it through the components that we chose. Then we will somehow aggregate, because we end up with 2 outputs, right? So we will somehow aggregate that and go to the next layer, right? So this going through the layers is the routing thing when we sort of choose this path. Okay, so we'll have these layers. Each layer will have a bunch of components. And then the aggregation part, well, let's say that it's just a sum or an average or a weighted average, something simple. So here we also assume that the components don't necessarily have to have the same structure. They don't have to be all fully connected layers, for example. But it's probably best if the output shapes agree. Otherwise, we will have problems when we try to average them out. Okay, so the routing algorithm is whatever will be choosing these components, right? Whatever will be sort of choosing which path to take in this larger graph. And then, as a rule of thumb, if we devise some routing algorithm, running a forward pass will be easy, because we'll be just asking which components should I run, and then just run them, right? So assuming your particular framework can into dynamic graphs, like PyTorch, for example, or new TensorFlow, then you should be able to do this. But then on the backwards pass, well, the components that you used will get gradients. The components that you didn't use will not get gradients. That makes sense. But there's also the routing algorithm, right? It will also have some parameters in it. It will also have to learn to choose good components. And that will be the part that will be hard to learn, right? That makes sense. The routing algorithm is making discrete decisions. So it makes sense that it's going to be hard to get gradients to it. Okay, so why should I bother? So there are several reasons why you could want to train these kinds of models, there's one reason that is sort of blatantly obvious, which is computational savings. If you have this large graph, but you are somehow able to choose a relevant part and only activate this part and not look at the other parts, then you can obviously get huge computational savings, right? Because you're not accessing the other parameters. So that's a pretty sort of obvious reason, but there are a bunch of other more vague ones. So you could say it's biologically plausible, at least in the sense that if you think about humans, we have our brains, which have a lot of parameters, a lot of knowledge in it, and then it seems that we don't necessarily use all of our knowledge for every input we encounter, right? If we think about the fact that brain has this sort of parts, and these different parts do different things, and for example, for vision, you don't use all of the parts of your brain, it sort of makes sense to have this, to not use all of your parameters for every input, I think. And then you could also argue that it's a regularization when you have a lot of things, but you can only choose a small portion of them for every input. It could be also regularization. Yeah?
So I have a question. Have you tried to use these methods for neural architecture search?
OK, so neural architecture search is sort of related. Yeah. So I'm not sure about using for neural architecture search. You can see sort of the relation when you have this bunch of components to choose from, and the components could be different things. So one of them could be a 3x3 conv, one of them could be a 5x5 conv. And you can only choose one, right? So in some sense, it's similar to, for example, the ENAS works, right? When the efficient NAS sort of chooses different subgraphs, here you're sort of choosing different subgraphs based on an input, right? So there's some relation there to architecture search. But it's different from architecture search in that in architecture search, you sort of search from some graph, and then you sort of train it, you evaluate it, then you try another graph, and here is all of this is sort of happening at once, right? You try one input, you go from one graph. OK, so how to train them on a high level? I think you can think about these two classes. This is not like a sort of official taxonomy, but I think it's reasonable to think about it like this. So some of the methods are kind of deterministic at heart, not in the sense that necessarily there's no noise, but some of the methods will rely on values. So they will have some values for different choices, some values for different components, and then if you have a bunch of values, it's natural to take an argmax to make a choice, right? But there will be some other methods will be not values, but probabilities, so probabilistic. So instead of having values, you will have some probability distributions over the possible things that you can do. And then instead of argmaxing, you will be sampling from the distributions, right? So that's some distinction that you can make. And then if you think about RL, you can, if you know what reinforcement learning is, you can probably see that it shouldn't be hard to apply reinforcement learning to learn this kind of routing. So just to give you an idea, if you take Q-learning, I would sort of put it on the left side because it sort of deals with values. And if you take policy gradient arc reinforce or PPO, I would put it on the right side because it's probability-based. But I will not go into RL methods here. So we can use RL. People have tried that. But we'll focus on methods that don't require RL and just train with plain gradient descent. So there will be no reward. There will be nothing like that we have to design. It will be just running a plain gradient descent, but somehow squeezing the gradient through the parts that are sort of hard to get gradient through. So there will be some approximations, but it will be standard gradient descent. So these are the two methods that I will cover. One of them is mixture of experts. It's sort of value-based. The other one will be the family of straight-through gradient approximators. I think it was already mentioned in some of the previous talks. OK, so the first method, so this is from an actual paper, mixture of experts. So we'll go through sort of a technical detail of how we could actually implement that. So you should be able to write it down as code after this couple of slides. So let's say that we focus on a single layer, which has n components. So here n is 4. We fix some k, which says we want to choose k components always. So let's say k is equal to 2. And we have some input x. So we will have this gating network on the side. Gating network basically means routing algorithm. So it will be the thing that will be choosing which components to run. It will be choosing based on the input x. So let's say that the gating network, it can be something simple, maybe like a linear layer. Applied to the x, we will get n values, so a value for every component. And then higher values which mean that this component is good for that input. So then let's say that we just take an argmax, right? So we take k, in that case, k is equal to 2, so 2 largest values. We run these two components, we pass x through these two. So we end up with 2 outputs, now we have to aggregate them. So that's the sort of tricky part that's actually very crucial. So to aggregate these 2 outputs, we will use some weights, so it's going to be a weighted average. And the weights we're going to get from taking the values that the gated network gave us and softmaxing them to get something that sums up to 1. So we had values 10 and 8, then we get softmax values 0.9 and 0.1. And we'll use these values to compute this weighted average. And it's actually this part, like the aggregation part is sort of crucial here. So why would that work? Why does that give us gradients? So the reason is that if we sort of average out these components with different coefficients, we'll get gradients to change this coefficient, right? So we will see, I ran these k components, one of them seemed better than the other, so I want to push up the coefficient for one of them, right? So I will get a gradient to change these coefficients on the right, and this will give me a gradient to change the outputs of the gating network. So in some sense, we're sort of using the gating network both for choosing the component and for aggregating, and the aggregating part is the one that is giving us gradients. So I think that's a crucial bit. And as a sort of side note, you have to choose k at least 2. If you choose k equal to 1, you can see that it won't work because you can't compare between one component. So that's that. And if you implement that, that actually works. So this does give you gradients. The gating function, the gating network does train with sort of standard gradient descent. So what we're really doing here, if you think about parameters of your gating network, say, on the x-axis, we're sort of changing these parameters. And for a given input, some set of k experts can suddenly stop being optimal, and some other set of k experts can start being optimal. So it seems that we're optimizing a discontinuous function with gradient descent, and that's true, that's what we're doing. So in theory, it could be sort of tricky that we change the gating function a little bit, and the set of experts changes, and something crazy happens. In practice, it's possible to make it work quite well, even despite these discontinuities. Okay, so now for a particular paper, for a particular result. So this was a paper from a few years back. So we applied this mixture of experts to a state-of-the-art machine translation model at that time. Machine translation, I mean, given a sentence in language A, translate it to a sentence in language B, so that's NLP. I think it was English to German or English to French. So I'm saying state-of-the-art at that time because it was pre-transformer. It was before the transformer model was introduced. So then people were crazy about LSTMs. Now they are more crazy about attention. So the model that had the state-of-the-art at that point, well, it had an input sentence, then some word embeddings, then many layers of LSTMs. So stack more layers, I think 9 of these LSTMs there. And then, so that was the encoder, and then there was the decoder part that also had LSTMs, and it was using attention on the output of the encoder. So that was the state-of-the-art model. So our modification was pretty straightforward. So we just removed most of these LSTMs, and we replaced it with this mixture of experts in the middle. So instead of having maybe 8 layers of LSTMs, you would have maybe 2 and this mixture of experts. And this mixture of experts was super simple. It wasn't recurrent. It was just a thing that was run for every time step separately. And the experts themselves, the gating function was linear. The experts themselves were either 1 or 2 layer networks. So something super, super simple. So that's what we did. And then a key point was that this mixture was super sparse. So we had several different sort of settings, but one of them was, for example, that we had 2,000 experts, and k was 4. So you could only choose 4 blocks out of 2,000 blocks, right? So that means that you were using 0.2% of the thing that you had. So the sparsity was super, super high. And we did improve the state-of-the-art with that. So this is, blue is some metric for machine translation. The higher, the better. So we did improve upon this previous state-of-the-art. And the training time was similar to that previous model, but actually the number of parameters was 40 times larger. So you think about, 200 million parameters, it's quite a lot of parameters. It's sort of a good size model. Our model had 8 billion, right? So even if you wanted to train it on one GPU and you didn't care about time, you probably wouldn't be able to, because you wouldn't be able to fit that on a single GPU. But even though it was so large, because of the sparsity, it was actually twice much faster than the previous state-of-the-art model. So that was sort of interesting. And then I think one sort of fun fact about that is that a year later, there was this transformer paper. So we sort of removed most of the LSTMs, replaced it with something simple. Then the transformer paper removes all of them and replaces them with attention. Actually, the guy that was overseeing this project, so the leader of our project, was also one of the big contributors to the transformer paper. That's sort of, you could see how you could get inspired in one of these works to get to the other, right? It sort of shows that maybe you don't need all of these LSTMs, and then it turns out that you don't need them at all. Okay, so some takeaway. So it seems, at least in some domains, so I would say NLP, there are cases when you increase your model and it just keeps improving your performance, right? And if you have this case, then it seems that having such a sparse model makes a lot of sense, because then you can keep the computation cost the same, but you can have more parameters for free, right? And then, well, obviously sort of skipped some of the details and some auxiliary losses to things to make it actually train, but if you're curious about that, you can ask during the questions part. So then a little bit about the other method. So this will be probability-based, so let's think about probabilities now. So again, the same picture. Let's say that we have this n components, we have some input, we have some gating network. Now we're going to assume that it produces n probabilities, not the probability distribution over n choices, just n independent probabilities. For every component, the probability, how much do we want to use it. So that's sort of, the gating network would be the same thing as we had previously, just with some sigmoid on the output or something like that. So then we have these probabilities. So once we have probabilities, it's sort of natural to just sample from them. So for every component, we will sample if we want to use it or not. So we end up with these zeros and ones that tell us if we're using this one or if we're not using this one. So then what we generally want to do is just take the ones that we used and sort of average out the outputs, right, and return that. We're actually going to do something a little bit weirder. So we're going to evaluate all of them, at least for the sake of this method. And some of them we will multiply by 1, and some of them we will multiply by 0. That seems that it doesn't change anything, because we just add some things that we multiplied by 0 that shouldn't matter. And it won't matter in the forward pass, but it will matter in the backwards pass. So we sort of aggregate all of these components with zeros and ones as weights. So let's see what happens on the backwards pass. So the red part is sort of non-zero gradient. So we will get gradients from the end, right, to the components of this average. Then we will get a gradient for the components that we actually used, right? So only for the 2 ones that we used. That makes sense. But we will actually get a gradient to all of these zeros and ones, right? So even if we didn't use a component, just because we know its output, we might get a gradient telling us, well, you should have actually chosen not a 0 weight, but something larger, right? So we'll get a gradient to change these zeros and ones, which seems sort of weird because these zeros and ones, you can't change this 0 into 0.1. These were just samples, right? But we still get that gradient. So now there's a question of what to do with it. So we had the probability, and then we sampled, right? And we got a gradient on the sample, which is this sort of red arrow. And then the question is what to do with the probability. So there's this trick called the straight-through estimator. And what it does, it basically assumes the gradient of sampling is an identity function, if you will. So it sort of applies the same gradient that you got. Okay, yeah. The same gradient that you got on the sample, it applies it on the probability. And that seems sort of hacky. And it sort of is hacky. It's a sort of a gradient estimation idea. But it actually seems to work well in practice. What we used is something a little bit more, a little bit smarter. And I won't have time to get into it because it sort of deserves another 20-minute talk of its own. But if you're interested, you can Google stuff like Gumbel-Softmax or straight-through Gumbel-Softmax. It's sort of, It's still the same setup that we want to sample and we want to backpropagate through sampling. But instead of doing something like this, there's a trick which sort of allows us to get both a hard sample and a soft sample. I know it doesn't make a lot of sense. You have to go through some math to actually understand it, but I would sort of encourage you to go through that. There's a, I don't know, like a 500 citations paper that sort of introduces this Gumbel-Softmax. So this is what we used, but we could have used that as well, I think. So in that paper, that was sort of different. So we're using multitask learning, but I won't focus on the multitask part. We had this data set, which is sort of cute. It's called Omniglot. So if you like MNIST, this is sort of MNIST for grown-ups. It also sort of recognizes characters, but instead of digits, you have 50 different alphabets, and it has, I think, like Greek, Cyrillic, some made-up alphabets. So it's pretty nice. So we use image recognition, recognizing these different kinds of alphabets. We had some deep convnet, I think 7 layers like this. Each layer sort of had different kinds of convolutions in it. And interestingly, the previous state-of-the-art on that dataset was also a mixture of experts, which was just by accident. Somebody applied a mixture of experts to this dataset and had a state-of-the-art. But it was sort of weird in that this mixture of experts wasn't really sparse. It was using like more than half of its component for every input. So it was very different from the previous mixture of experts, which was super sparse. So what we first did is we sort of just kicked out the routing entirely. So we modified their model, and this was their model. We sort of copied that. We modified their model to not use routing at all. So just always use all of the components and just average them out, so with equal weight. And this already was better, which was weird, right? So I guess one interesting takeaway here is that maybe some ablations of state-of-the-art models actually get you better models. But then we tried routing a little bit. So we used this kind of straight-through Gumbel-Softmax routing, and we were able to push the state-of-the-art a little bit. So that's the new state-of-the-art. And then I think a takeaway from this one, so this set of experiments was very different from the first one, is that with NLP, I said sort of you have infinite data, so you can increase the sizes of your models. Omniglot actually is super small, like the amount of actual images is very, very small. And it seems in this setup, it seems harder to get these sort of gains from routing. And I would argue that it's still possible, but maybe we need less hacky methods to sort of apply these routing models also to the small data part. That seems certainly more challenging than the big data part. And that's pretty much it. I have a slide that says future, but I don't know what the future is going to be. I can just say that I sort of know smart people at Google that are excited about these kinds of models and that are working on these things. So I would sort of imagine a stellar future. I think we're going to see nice results maybe next year, and I hope when you see some model that looks kind of like this, has this sort of routing conditional computation thing in it, maybe my presentation help you sort of understand that new work. With that, questions?